Hi, my name is Manish Gupta, and in this video, I'm going to talk about Gemma 3 model from Google. So let's get started. How is Gemma 3 trained? Well, Gemma 3 is a standard transformer decoder model, more or less with the same architecture as Gemma 2, but it has a few differences, and which is what I'm going to talk about in this slide. So on the left side, I'll talk about the architectural differences. On the right side, I'll talk about the training recipe. Okay. So on the left side, as you can see, it has been trained using grouped query attention with post-norm and pre-norm with RMS norm, which is, grouped query attention has become pretty popular rather than doing full multi-head attention. So that's that, and it uses post-norm and pre-norm. To basically reduce the KV cache memory usage. So you see, I mean, if you train models with longer context length, then the amount of key value cache usage basically increases significantly. To reduce that usage, they basically interleave local and global layers. So for every one global layer, they have like 5 local layers. Now, local layers are the ones where you have local attention. Global layers are the ones where you have global self-attention. Okay. So on the local attention, what does that mean? So that basically means that for every query, rather than paying attention to every key in the input, it basically pays attention or does self-attention computation only with 1024 other keys in the input. So local layer basically works on a 1024 sliding window in that senses, while the global layer obviously attends to the entire input, which in case of these kinds of models is basically 128K sized inputs. Max input context window is 128K. Okay. So as you can see from the figure here, you see this is for the 2 billion models. So in fact, Gemma 3, it exists. There are 4 different models which have been released, 4 different sizes: 1 billion, 4 billion, 12 billion, and 27 billion. The Gemma 3 models are also multimodal and multilingual. So as you can observe, the 1 billion model is not multimodal, but the other 3 are multimodal, and they use the same vision encoder. Okay. In fact, they use the 400 million sized SIGLIP encoder, vision encoder, which takes a fixed input size of 896 cross 896 pixels, and it is kept frozen. So you basically really treat it like a preprocessor in that sense. So the number of parameters obviously are like 1 billion, 4 billion, 12 billion, and 27 billion. So if you look at it, 1 billion model is also English only, it's not multilingual. So the 4 billion, 12 billion, and 27 billion are multimodal and multilingual, while the 1 billion one is not multimodal, it's just text only and English only. Okay. The 1 billion model also has a smaller context length, just 32K context window size, while the other 3 models, the larger ones, basically have 128K context lengths. So while doing these long context lengths, essentially they also increase the frequency of the rotary position embeddings from 10K to 1 million on the global layers. So on the local layers, it still stays at 10K because you just have 1024 tokens to pay attention to, but on the global layers, they increase it to 1 million. Also for the smaller model, you basically don't need to do that because that's just basically 32K sized input context window. Yeah. So overall, they use sentence piece embeddings with multilingual vocabulary of 256K, covering 140 languages. For the vision modality, as I mentioned, they basically use the SIGLIP vision encoder with 417 million parameters, and they keep it frozen. Now, the input size is also fixed 896 cross 896 pixels, and that can cause trouble with different aspect ratio based images or images which are much larger. And therefore, they use this pan and scan approach at inference time. The idea is very simple. You basically take the image and tile it. Tile basically means, take multiple crops which are disjoint from the image, divide it into, disjoint tiles in that senses, and then, you resize these tiles back to 896 cross 896 and provide them as input. It's also called as adaptive windowing in that senses. Okay. So now, as I was saying, yeah, I mean, if you have very long context length like 128K, then you basically need to be careful about the overall key value cache memory usage. And what they do is rather than having these global layers, they basically interleave global layers with 5 local layers, right? So one global layer, 5 local layers, another global layer, 5 local layers, and so on. Now, what does that do? So how does it really save the key value cache memory size? So this is a picture which shows you how the cache, how the overall memory size cache usage reduces thanks to these global local kind of layers and also local attention in that senses. So this picture is basically for the 2 billion model with max sequence length of 32K. So as you can see, for a global only model, the model takes the model embeddings and weights basically take the red kind of space, and the yellow kind of space is taken by the key value caches, right? And it is a very large key value cache of about 2 GB, right? But the next 4 bars basically show how things improve when you actually, add more and more local layers, local attention. So for every global layer, if you add one local layer with a sliding window of 4096, the cache basically almost reduces to half, right? But then, here there is one global layer and 3 local layers for every global layer with a sliding window of 1024. You can observe that the KV cache size is very small, less than maybe like 300 MB or so, rather than 2 GB in the global only case. Okay. Now, the training is done in 3 different steps. The first step is pre-training, and the pre-training is done using much larger amount of data compared to Gemma 2. So 14 billion tokens for Gemma 3, 27 billion, and 2 trillion tokens for 1 billion, and other sizes accordingly, right? The pre-training is done using distillation. So the distillation is done using a much larger teacher model using cross-entropy loss. But obviously, if you use 256K logits, that's going to take forever. So therefore, they basically use 256 logits only, right? So they use just 256 logits and basically do distillation from a larger model while pre-training. Max sequence length is increased in stages. So in the for most part of the pre-training, they basically use 32K as the max sequence length or the input context window size. But then for the last part of the training, pre-training, they basically increase it to 128K, which is typically done in most model training as well. Some people also call it like the mid-training phase, right? So that's how it is done. After this pre-training part, though, there is a quantization-aware training that is done so as to reduce the model size even further. So, and this part is done by fine-tuning for 5,000 steps. The fine-tuning is basically done such that you use quantized weights, but then you use the probabilities from the non-quantized checkpoint as the targets. So that's basically what is called as quantization-aware training, and that's just done for a small amount of time, just 5,000 steps. Quantization is done using 3 different formats. So per channel int4. So basically per channel, you take the weights and do int4 quantization on them. Per block int4, and also switched FP8. So switched FP8 basically means you can basically choose to have E4 M3 or E5 M2, basically having 1 sign bit and 4 exponent bits and 3 Mantissa bits, or 1 sign bit, 5 exponent bits and 2 Mantissa bits, right, per layer. So for every layer, you basically decide which is the format that you want to use, and then you use FP8 basically. Yeah. So that is what is done. Now, obviously, this leads to several checkpoints, and all of those checkpoints are publicly available. So, Gemma 3, Google has made all of these checkpoints publicly available for all 4 model sizes, all different kinds of quantization, even the pre-trained checkpoints. All of them are publicly available, including the instruction tune checkpoints as well. Okay. So the instruction tuning is done as part of post-training. So post-training does 2 things. One is instruction tuning, and then reinforcement learning. So instruction tuning is again done using knowledge distillation from a much larger instruction tuned teacher. And then reinforcement learning is the next phase as part of post-training, which basically helps the model improve helpfulness, math, coding, reasoning, instruction following, and multilingual abilities, making sure that it is less harmful. Now, for reinforcement learning, they basically use trained reward models, trained using human feedback, human labeled data, or also automated reward models like code execution based feedback, or standard ground truth, which is available for several math problems. So that's how Gemma 3 is trained. Now, how does Gemma 3 perform? So Gemma 3 has been benchmarked against several standard benchmark data sets, multilingual, multimodal, and text only as well, right? So on the right side, what you see is basically the results on the LMSys chatbot arena leaderboard, right? In terms of ELO ratings. And what you can see is Gemma 3 27 billion instruction tuned model is actually very much comparable to other models which are way larger. I mean, even closed models like O1 or ChatGPT and so on, right? So in terms of ELO ratings, it is way better than the Gemma 2 model that you see here, and way better compared to even Llama 3.3 kind of models, right? So now the point is that Gemma 3 27 billion is much smaller than many of these closed models. So it's basically a small model, but gives you very good results, very good quality results, right? So this chart at the bottom basically compares Gemma 2 with Gemma 3. And 9 billion model with a 12 billion size. And what you can observe is that Gemma 3 is way better on various kinds of abilities or skills like coding skills, factuality, reasoning, science, multilingual, or vision-based skills, right? Also, you can also look at the detailed results here. So Gemma 3 versus Gemma 2 versus Gemini versus Gemini 2.0 and Gemini 1.5. What you can observe is that the 27 billion parameter Gemma 3 model is very much comparable to the Gemini 1.5 Flash model. You see, so 67.3, 67.5, 8.6 and 10 and 82 and 74. So basically, it's very comparable. It's not as good as the Gemini Pro models. I mean, Pro models are way better. But from a model size perspective and from the perspective that it is made openly available, Gemma 3 models are really good, right? Okay, so that's yeah. I mean, and here is an example of interesting things that Gemma 3 could do. So given this receipt, and the question, I only had the sliced meat. How much do I need to pay? Include a 18% tip. It could actually do some good math here. So it could basically understand what sliced meat means. So it could basically figure out that, hey, this thing 1x whatever this is, right? I mean 1x of that is basically sliced meat plus a side dish of fried potatoes. So it takes that. It takes the price for that 36.5, and then it adds an 18% tip as asked by the user, and then gives you the final amount. Right? So that's it for this video. In summary, in this video, I talked about the architectural changes in Gemma 3. Primarily, Gemma 3 models are available in 4 sizes: 1 billion, 4 billion, 12 billion, and 27 billion. The last 3 models are basically multimodal and multilingual as well. These models have been trained using long context length, where the input context window is 128K. So it's a very long context model in that sense, right? And these models basically can fit on a standard 32 GB GPU, thanks to the quantization that has been also done for these models. They involve 5:1 interleaving of local versus global layers, where for every global layer you have like 5 local layers with much smaller local attention sliding window. And in terms of performance, well, they perform much better than Gemma 2 models. They are small, but reasonably good in performance. Okay, so that's it for this video. Thank you for watching. Connect with me on my LinkedIn and look at my research on my homepage. Thank you.